Okay, so in this lecture, we will continue with the topic of decision tree. And in this topic, we will go over what is decision tree and how it works, and also how it performs, and including how it's implemented, and finally the advantages and disadvantages. So again, decision tree is a classification, is a tool for classification, but it can also be used for regression as well. So why we want to consider this tool? Okay, let's consider this example where you have the training data, where you already know what or how the data are aligned. Like for example, you have the data points that are labeled as stars. Those star points belong to class B, let's say, and the bold points belong to class A, like that, right? And they are training, so you already know. But the thing is, if you use or apply tools like linear SVM, you may not be able to separate this kind of data because the data points that belongs to class A are somewhat like they kind of overlap into the line to the side of class B. Like if you draw a linear line like that, you can't quite separate it. You need two lines, or maybe you need some nonlinear decision like that, right? You may have to go over the nonlinear SVM classification in order to classify these data. But in this example, okay, to make this simpler, we will be learning this technique called decision tree, which will be able to separate the data with nonlinear decision. And this will be done by, let's say, it's like the core idea of decision tree is to divide data points into regions. And that data points are referring to the feature, the data point of the feature planner. For example, you have a set of training data, right? And you have feature denoted as X and Y. Here's a label. Let's say if you're XJ, and in this case you have like 12 points, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 11, 12. Thing is, what is YJ? YJ is a label, and XJ is just happen to be onto the planner, right? So you can plot it onto the planner like that, where the axis for X1 is above, X2 is down here. And then the way the decision tree would do is that they will try to find a region that divide these data. For example, the region could go this way, like that, and that, right? And then you have like 4 regions. R1, sorry, I'll just use normal pen. Maybe R1, R2, R3, and R4, where if you divide region like that, you divide data into separate region, and you say, oh, data in region 3 and 4 must be like in class B, and data in region R1 and R4 are going to be in class A. So whenever you're testing sample, let's put this as a green color, where you wouldn't know, like let's say this is the testing, right? You don't know which class it is, but if it fall into region R4, then immediately you will infer this as being class A. But if you are testing somehow fall into the region R2, then immediately you say, okay, must be in class B. So you use the region that you created from the training to infer what is the class of the testing data sample. So that is how the decision tree work. And yes, this also means that it has to learn how to separate these regions from your training set. Okay, and this is the core idea of decision tree, but people actually refer to decision tree as more like the algorithm to solve this problem. Okay, so let's state the problem properly. So in this decision tree, the objective of the decision tree algorithm is actually to construct the region R1, R2, up to R3 such that either it minimizes the residual sum square or it provides the lowest error in probability of data that fall into each region. For example, if you think about that, if it happens that this testing data is actually in region R2, so this means that, okay, if it's in region R2 and it actually came from class B, this means that the region error is going to be low, right? It's going to be 0. But if the testing happened to be actually came from class A, then that means that, whatever here, it gives you the wrong inferred class, and that gives you high error. So that is what it means by the classification error rate. And this rate is per region. So we want to construct the region as best as possible to our knowledge based on the training data. And we will then use this region to infer the class for the testing sample. So that is how the decision tree would work. Well, I believe that this is going to give you like a good view of what classification look like. But what about regression? Regression would work slightly different. Let's say if you have data points, but in this time when you have training data points for regression task, you don't really have it with class, but you have it with value that you want to infer given the input feature. So what you are doing is that you are trying to find the value that is representing the region. For example, let's say if the darker blue are representing the higher value. So, and if you could divide the regions such as this, R1, R2, and R3, maybe, the value that could well represent R2 is the average of these points. Then you have like a y hat R2 being the average of this guy, like divide by 1, 2, 3, 4, 5, 6, 7, right? Or again, you may be able to find the representative of this R3 as the average of the region. Divide by 4 this time, and this one is going to be divided by 4 as well. And the thing is, as you move the region, you will have different value for your representative value of each region, but you want to make sure that whatever regions that you choose, you give this lowest possible error with respect to all the yj in that particular region. So this value, like in a very first sense, it could be like the average, right? It could also be like a mean, mode, max, right, of those regions as well. But this depends on your objectives, like what you are looking for in that regression task. Okay, so that is like a problem setting of the decision tree. Then we will build a tree. Okay, I think we now know what is the problem setting, the problem definition of decision tree, but I believe that lots of people would ask, like, then why we can't solve equation 1 or equation 2, which are these two equations, directly? The answer is that it's not easy, because once you move to one particular region, likely you're going to change the answer for the rest. Or maybe this one, let's say if you have to move this line up, right, then maybe some of those points will be moved toward the others, and then you have to recalculate everything again. So it's a hard problem to solve in real time. So with that, people actually come up with the greedy algorithm or decision tree to solve these two problems. And these greedy problems these greedy approaches are going to be what we call a recursive binary algorithm. And we specifically in this lecture, we will just focus on the one with the binary splitting. I will not go over the other type splitting because it's not easy to illustrate, but maybe if you have some time, I will recommend you to go over like a website that could actually show you what the binary tree would look like with different configurations. But that one we will provide you the example at the end of the class. But right now, let's go over what is decision tree like as the algorithm. We now know the problem setting. The problem setting is that we want to maybe classify data or maybe do the regression, but the way that we do it is to divide the data into partitions or maybe into regions, and the decision tree will try to find the best possible region such that it minimizes either the residual sum square error for regression task, or for classification task, it will try to reduce the classification error rate, which is like 1 minus the probability of that region. Okay, so that is it, right? But now we will go over like, so how would we build this region if we wouldn't solve these two optimization problems? Okay, so before we go over how to build those regions with decision tree, let's define some components in the decision tree. Okay, firstly, we have a tree, right? A tree will consist of node, but there are two types of nodes that we are considering. One is leaf nodes, the other one is decision node. Okay, so the first one here is actually also decision node. So it's like, firstly, when you have a bunch, maybe a set of training, right? And you want to decide, like find the region, the first thing that you would do is that you make a decision, right? How to partition the region. And that will be the decision node. So node in the decision tree is more like a stage of the operation. If it was called a decision node, it's usually referring to the time where you want to apply some decision to divide the regions, okay? To divide, sorry. It's like, it's in a state where you want to divide the region. But if it was a leaf node, this means that it is a state where you want to assign the final value. It's like you assign the value to that region. Like when I said that, for this region, I want this to be the representation. Or, for this region, R3 is representing the rate, the star points. So it's probably class B, or this region is class A, this region is class A, this region is represent for class B. So that is what the leaf node is. So it's like it's assigned a value or maybe assigned the representation of that region. So it's a state where you do something. Okay, so what are these nodes? Specifically. So the decision node will contain a threshold value. Well, of course, if you have to divide, if you want to divide it, divide the regions. So yes, you have to have a threshold. Right. What else? Decision node is what we call a root node. Yeah. Okay. So another word that you would probably have to hear is that any nodes, right? Any node, if it has child like this, the red is the child or children node, maybe like a child node. This is a parent node, and it's also called root node. Yeah, so that's the vocabulary. Right. And of course, if you have children, right, you have to specify what are those children's. Well, the child nodes will have the left child and the right child. Okay. So the decision, so the way we assign the left and right is just, like if this is on the left, then it's a left child. If this on the right, then it's a right child, just like that. So parents node, that's the one up above. Left child is the one on the left. Right child is the one on the right. And the child node can then become a new parent if it just turned out that you still have to make decision. Or a child could turn to be just a leaf node if there's no further decision needed to be performed. Yeah, so it depends whether or not, the left child would turn into a decision node to be another parent, and, then we'll have a child again. Okay, we'll just, further split like that. It depends on, whether or not a decision is reached. So yeah, the way the tree grows depends on, how we design the algorithm. And for decision tree, there will be some kind of rules that will make the tree grows, right? And yeah, again, the leaf node will contain value for classification or the value that we want to assign or represent it. And leaf node is also a root node, but it doesn't have any subsequent, or in the other words, it doesn't have child. Okay, you can say it's a root. I don't want to call it a root. Maybe I would like to omit this one. It's a little, too much of the vocabularies, but you now know the leaf node is the final one where you cannot further split. Okay, that's it. All right. And one big tree can contain multiple small trees, like for example this one. One big tree, and this is a small tree. Can you see another two small trees? This one is another small tree. This one is another small tree. Okay, a small binary tree consists of two children. Yeah, left and right, left and right, left and right. Yep. And actually, one thing that you should notice, well, when we say, we have bunches of data that we want to, then we would divide it, etc. In fact, if we think about those, those data samples that are left at the leaf, that means that, the leaf is representing the operation that will be done on a set of data or that particular regions. For example, if you have decision tree that is written as follow, that is, let's say you have a set of data points, right? Okay, I'll just erase the regions for the time being. Okay, you have a set of data points like this one, where everything together, if you consider them, is like this first blue blob. Okay, I'll remove this one. It's like this one, right? Then you further split it. Let's say if you want to split it, but I know the rules of how, decision tree works, so I will just show you a little bit. Let's say if you make a decision and you split this out, right? Then this one is kind of independent and you call it the region R1. Then you will assign this region R1 as a leaf node of that decision tree. Of that decision node or of that parent. Then the rest of that will be another decision to make. Let's say you make further decision And as it turned out, well, this time you end up having R2. Then let's say this is your R2 being your, like another leaf that you get, but you still have these group of nodes that you still cannot decide. So then it become like another decision node, right? But this time, maybe the way that you make decision is slightly different. Maybe you make decision along the x-axis and then you can divide it like that. Then you have R3 and R4. Then yeah, you kind of get the, let's say maybe R3 and R4. So you can see that nodes somewhat correspond to the regions. These nodes, right? These nodes somewhat correspond to the regions that you divided. Okay, so sorry, just notice that. Okay, I'll just use a different color. So maybe these leaf node. Okay, I want to exclude that red one out. These leaf nodes somehow correspond to the regions. So another thing that you should know that when we refer to nodes, you should also think about regions of how the decision is made, right? Okay, and before we go over the algorithm, I would like to give you a definition. Like, you probably wonder why this is how I divide it. Well, actually, this is how the algorithm would work, one way. But before that, we have to just go through a few things. When we want to assign the value, right, to the leaf, like that one that belong to one class or the other class, stuff like that, we say that, for all the points in the leaf, if the majority belong to one class, then we will use that majority as a representation for that leaf. Likewise, for the regressions, we may use like a simple operation like the average of those value in that particular regions, which are the leaf. Then we will assign the value that represent that leaf. Okay, you can do it this way. And also, another thing that you should know before we start the algorithm is that right now we consider only binary splitting. That means when we have a decision, right, we would only divide it at half, right? And the diameter of the tree or the width of the tree is like how far apart from the first to the last. Yeah. It is another hyperparameter is decide how many times you want to do splitting. Let's say if you further do splitting, how far the splitting would go. And the splitting threshold, this one is actually the model parameters. These two are hyperparameters. They are parameters. Okay, for the hyperparameters, they are the parameters that you have to set it before running the algorithm. But for the model parameters, they are going to be the parameters that you will learn throughout your, okay, they are the model parameters are going to be the parameters that your algorithm will figure it out as it run, as the algorithm goes on, right? Okay. Okay. So this is going to be how the coding would work, but the thing is, I don't want to go through this first because it could be quite confusing. But let's define something before we actually go over the algorithm. Okay, node purity. Node purity is something that we use to group the region in decision tree. The purity, if we are talking about the regression task, is actually the variance. The variance of the value in the data points of that regions. If the variance is high, then the node will have lower purity. Likewise, for the case of classification, if the entropy or Gini index is high, then that node is less pure, or the purity is lower. So let's look at the reason why we define this. Okay, before first, because when we do classification, we want to make sure that if we want to make a certain classification that would generally applicable for your data set, right? That regions that you divide, like for example here, I'll just go back to the first example, like this one. You want to make sure that regions that you divide would work not only in your training but also in your testing. So very likely the way that you make decision, you want to make sure that that region, let's say R3, will have the node in class B as much as possible, because you want to group those points in the same class together, because the chances that when you do the inference on testing data, or maybe when you deploy this model, you would assume that the distribution of your data in training should be the same as in your testing or when you deploy. And therefore, for a sample that just arrived to your algorithm, you want to assume that it had the same distribution as just training, therefore this one will be assigned to class B, right? Because it's just going to be the same as the majority of those points in that region. So in a way, we want to define purity to define whether or not that region are containing the node, to define whether or not that regions is containing the data points from the same class. It could be either class A or class B or more. When we do classification, especially in binary trees, it could really, let's say if you just imagine if this one is happen to be like another class, let's say I will just draw a flower. And this is the data sample of flowers. Then it would work, right? You could classify more than 2 classes. But it's just that the class 3 is in region R2, and you got class A, okay, YJ maybe in class C. It just happened that, class B are in R3, class C are in R2, and for class A, it could be either in region R1 or R4. It could work as well. So it worked for multi-class classification. Naturally, you don't need to do anything about it as much, but you just have to find the region that contain most of the samples in one class. So with that, we define the purity to measure whether or not this region are containing the samples from the same class or not, or would you be able to find a better splitting that you will give this set of these samples to be more pure, or it contains points from the same class more than the other types of splitting. So that is why we need purity to check this. But purity for classification is different from the one of the regression, and for the classification is defined as follow. For classification, you can use 2 matrices to measure this purity. The first one is the entropy. So it goes as this, formulation. For Gini Index is another way to measure the purity. And again, be careful. The higher the entropy or Gini Index, the lower the purity, and we will see why. I think the easiest way to see why is that you just get this function and vary the value of p, right? And you know the p is the probability value. You can vary it from 0 to 1. And you will see at which p value that give you the maximum entropy. And it's turned out that, at about p0 to 0.5, it will give you the highest entropy. At p equal to 0.5, that means it's just half. It's like the points in that particular region can be either class A or B equivalently. So this means there are high mixed of data between two classes. Therefore, it has low purity. On the other hand, if your entropy is low, like at 0, but p could be either 0 or 1, that just means, that the samples in that regions are either class A or B, and just that. Like it couldn't have the mix of the two. So that's the meaning of the entropy. And in fact, you can do the same with Gini index. And this is what I got. I actually, just do the plotting normally. You can see that, well, Gini index actually have a lower value, but the maximized value of entropy and Gini index is actually happening when p is equal to 0.5 at the same value. So this is something for you, okay? Actually, I would recommend like a YouTube video for you to watch and to see like how to compute this value and how would you judge. But I think mostly the way that we use entropy or Gini index, we use it when it's not easy to make decision, and we use it when we want to do the programming, because it's like we don't have the eyes to look at the data distribution, like the overall distribution, to find the regions. And you will see why we kind of need these values when we do programming, rather than solving problems in algorithmic way. So that is something for you. Okay, in terms of regression, the purity is defined by the variance. I think you can assume, you can guess why it's the variance. Like the higher variance, the lower the purity. And the answer is, if that region gives you various possible value, of course, that various possible value yi here, if it's subtracted by the mean of that, it will have like a lot of dispersion. Therefore, the variance will be high, right? And yet again, if you want to see whether or not threshold A or B is better, you probably want the one with the lower variance. But thing is, the way we define whether or not this splitting is better, is improving your algorithm, is kind of measuring with respect to the parent. Like if in the parents you done some kind of thresholding before and you got a variance value, then what you want to do is that you want to make sure that the child is giving the lower variance. And when the child is giving the lower variance with respect to the parent, that means you have a high reduction, right? When you have a high reduction, that means that new thresholding value is better. So this for this, I give you this example. Like here, the 0.45 are of the, so they are the variance of the parents. And these two are actually more like two variations of how you want to divide your child. Like there's option A or maybe option 1. It gives you some reduction, which is 0.04, versus the other one, it gives you a higher reduction of 0.14. So of course this one is going to be better because this gives you a lower variance than your parents. And that is like a better splitting that are moving forward to, and it will give you higher purity because the variance is lower, therefore the higher purity towards the end of your algorithm. So that is how purity is being used. So yep. Okay, so I think before we, and again, yes, for classification you have the same way of deciding, like you have the entropy of the appearance, and then you have again entropy of your child, like you may be having two ways to divide the child nodes, and then you probably want to choose the one that give you the more reductions, right? Okay, I hope that you wouldn't confuse the higher reduction, or maybe this is called like a higher gain for higher reduction, a better reduction. And yeah, but for the regression task we call it the reduction. Yes, so higher gain give you the better splitting. Again, higher reduction give you the better splitting, but don't forget the fact that higher reduction came from the fact that the new splitting is giving you the lower variance, therefore the node is giving you the higher purity. Likewise, for classification, you get a higher gain. That means that your entropy is the new entropy that is done, the new entropy that could be calculated from the new splitting of the child node. If it's give you like a better splitting, that means it's gonna give you the lower entropy and therefore the higher information gain. All right, I hope this not confuse you, but okay, let's see the example. Okay, let's start up with you have a training set of data. It's spreading like this. Okay, please look at this YouTube video. I do recommend it because I actually adopt
Hello, people
this
from the future.
example from
Welcome
this
to Normal.
guy. And actually, if you were interested in how you want to implement this algorithm, feel free to watch his video
The
on
leaf
how he
node.
implemented and maybe go over the coding to see how this is implemented. And you will see how information gain and variance reduction are being used in his codes. Actually, what is good about this YouTube video is the fact that he actually provides you, like the coding sample for both classification and regression, and you will see that actually they are pretty similar. But the difference is the only the operation that is done on the leaf, and how the information gain and variance reduction are calculated. So that's the only differences. Okay, let's just go back to our slides. Okay, so at first you have a set of training data, and it's labeled, like let's say the red node is probably class 1 and the green node is in class 2, and you want to do the splitting so that the result from the splitting will give you the regions that contain, like where each regions will contain the node that is as pure as possible, or on the other words, they will contain the nodes. These regions will be the nodes that will contain only data points that are having the same class in each region. Okay, so at first, let's say if we want to do the splitting along x0, this is algorithmic wise, right? So we just browse through this direction and we'll see, okay, at which value of x0 will I have the splitting that give me a group of data samples that are in the same class? And the answer is this one. Like, it's simple, right? It's like you increase the threshold and you found that, okay, maybe around here, that is like the first step. Okay, so I will use this as the first decision. Okay, and then it is, right? Here's my first decision. And notice that actually, to make it more practical, the way that you sort for this value for making decision should somehow it should somehow detect it based on the data samples that is available, right? If you would just scroll all over the value, it would turn out that you sort for infinite many value on the real space of x0, which you don't want to do that. And the easiest way is actually to track along each point, and it's just turned out at this point. If you split it here, you will get a region, at least a region, that is containing points in one class, and the other region is containing point of the others. And, well, at least this region is giving the node is pure, right? So you will do the splitting here. And again, when we do splitting, that means that this action of splitting become a decision node, right? And then you write what is the value of x0 that you would make a split. One thing that you have to be careful about is the fact that when you use the notation of less than equal, then for every decision you also have to do less than equal. It's better, right? So let's say you do the less than equal, and if those value of x0 is true, then maybe you put it on the left, right? And here you get it on the left. This is your leaf. Okay, and as you can see, the leaf node is the one that contains only the samples from the same class. And then because it's a classification, you could run the majority, and the majority will return red. Okay, so this is representation of your first region, R1. Then the question is, what about the other region that you know is not pure yet? Well, you can further process this area by maybe ignore this guy for the time being because you already made a decision about it. Okay, and then what you do is that, okay, so you would do the same thing. You come with a thresholding bar, sort for each value, move so until here. Again, it just turned out that when you reach about this threshold, it turned out that you actually get leaf node that is pure, that is here. So yeah, maybe this is when the value of x0 is equal to -9 and made it up. Okay, -9. And for those that is true, is still having some mixed nodes together. Therefore, this will be like another decision node. But for the one on the right, which are these, they are pure now because they only consist of the points from the same class, right? So, and the majority of it is red, so the answer is the leaf is red, right? And it will further continue to process this area, right? But in this area, you can no longer divide it by, splitting along x0 anymore because, it's mixing now. All you do is maybe go along the x1, and it just turned out that if you move this up a little bit until here, about here, you can split it into two regions where one of the region will be like all red and the other region will be all green. So now you have like, and if you use like a less than or equal sign here, you see that for those that are true, that is green, it can no longer be able to be divided. But for the one on the red, you get the same conclusion, like they are red and there's no further decision to be made, so you can stop. But the thing is, the reason that we can can split this and further refine the result is probably because we didn't say that this tree will have this many tree width. Like this one has about 1, 2, 3 tree widths. But if you restrict it to 2, then that means that for the rest of the region, which is this region, you have to do the majority test. Sorry, you have to find the majority, and it could turn out that the majority is green, right? Like out of here. But because this time we didn't say how many times we want you to do it, so you can go further and further. But when you do the programming, you have to set up this number, because otherwise your algorithm could run forever. Okay, so that's how decision tree works. Simple, but well, okay. So I think before we end this lecture, I will go back to the slides that I haven't described, which is this one. And it's the same as the one that I put in the last slide. That is, when we build from a small tree to a big tree, when we do the training, at the first step, as you see the example, at first, we assign whether or not we want to check this out as a decision node or leaf node. Thing is, if it's a leaf node, right, it should contain only pure nodes. And for your first step of decision, it could be a decision node if you didn't say that you want tree width to be 0. On the other word, if I mention that the tree width has to be 0, then will automatically become a leaf node. So this is something that you should keep in mind. Okay, we first start with whether or not this is a decision or a leaf, but usually the first one would depend on how you set the tree width. Okay, if we say the tree width is about 4, so we can continue our routine to check whether or not we can make a decision, or are these nodes pure leaf. And it could just turn out okay, if this is all red, right, then it's just pure leaf, then you get the answer. But if this is not pure leaf, if this is like a mix of points from different classes, so that means that, okay, we have to do something, we have to run something. So we have to have the child. And we know that there are 2 possible child, either the left child or the right child. Then we're going to find those 2 child by sorting over value. Then that's value of the feature. It could be x0 or x1, right? So if it's sorting along x0, and it just turned out that, it could find a region that provide one pure leaf, then, that region will be a leaf node automatically. So that is how the algorithm will go. But as you can see, once you have the leaf, right, and you left with the decision, the algorithm will start again in this region. But it will start as if it's never seen this area before. So this means that, like if it could start like just consider this region and ignore entirely the one that we already made decision. We go over this again and then divide it again and here again. This means that all these procedures are recursive, and therefore we could write the recursion as follows. So at first, you check if you can split the data. If you can split the data, then that state is the decision state. Then that root node will be assigned as a decision node. And we find the best splitting to separate the pure child. As you've seen before, like when you find a value of x0 that gives you the like a region that contain set of points that are from the same class, then that is pure. Then you do the splitting. You collect that splitting value. Then you assign the left and the right. Usually, the left will be the one that satisfies that thresholding condition. Maybe the thresholding is maybe x under that threshold is true, something like that. And you would then assign whether or not that region belong to the left or the right child. And when that is done, the procedure will start again. And when the procedure starts again, it will start to browse into each child node. Let's say if that child node happen to not be able to give you any decision because it's already a pure node, so that one will be a leaf node that you have to do some computation to assign the value to that leaf node. But if it's not, if it's it's a mixed and it's not pure enough, let's say, you will still need to go over that node to do the procedure as it's a decision node, to do the further splitting, assign left and right, and on and on and on. So it's just like this diagram where at first, is this a decision or leaf? If it's decision, then it has child, two child. Is this child a leaf or a decision? If it's a leaf, it's a leaf, we assign it. If it's a decision, then we further split. If we split it, we have left and right, and we go over maybe the left one first, and then we check if it's a decision or a leaf. If it's decision, then you have left and right, and you check another one. Is it a leaf or decision? Because yes, it's possible that you may end up having this one being another decision, and then you have another decision. That's fine as well, but that means that these two are not that pure. Okay, but it's possible. Actually, the example that I provide at the first slides could be the one that you end up with this. When you have like that are exactly around the same value. This one. If you have data like this, very likely at your first trial when you try to sort for let's say x0 that give you pure, it wouldn't give you pure. Or when you do the sorting for x1 that give you pure, it wouldn't give you pure. Then pretty much you end up with something like decision, then decision, and then you end up with having 4 leaf. Yeah, so this is for this case. So I hope that at the end of this lecture you will be able to grab the idea. But okay, I actually will have one question in the final exam asking you to do something like this, like to do the decision tree splitting. And so this is quite important. It is recommended you go through the video that I just showed, and like to check whether or not you understand what the video said as well. It's going to be quite similar to what I just said. And also another thing, okay, not yet, but maybe in the next lecture we will go over some examples from the website that show you how the tree is built. But don't worry, we will learn about it. Anyway, I think at the end of this lecture, I think you probably able to grab some idea about what decision tree is. But the thing is, there are some drawbacks of this algorithm. That is, if you happen to have the testing samples that are quite different from your training, let's say if your data don't really align with this, data distribution as in your training. Maybe, for example, if at testing time, it just turned out that you have a lot of overlapping of the class, of one class to the other like that, decision tree would fail quite easily. So there's a way for saying this kind of problem in decision tree that is called overfitting. On the other words, it's actually overfitting to your training. Okay, so that's like number one problem in decision tree. Also, yeah, it's unstable, any small change. The longer tree width would tend to have higher variance and lower bias. You can think of longer tree width like the regression with lots of model parameters. And the shorter tree width is like regression with a very minimal number of model parameters, like that. It's the same way of thinking. And yeah, as you noticed, the decision tree gives you some kind of non-linear decision line compared to the linear regression. So that means that it actually have higher variance compared to the linear regressions. So this is something that you should notice about. Okay, all right. And yeah, the good thing about tree is that it's easy to be graphically displayed. But the thing is, if the tree width is long, right, and that means your decision become more and more complicated, that is when the decision tree will no longer be visibly understood easily like it used to be. So a lot of time these types of algorithms will have some kind of issues where if you let your algorithm to grow so big so far away, it's not easy to analyze its performance as well. So it's like the complexity will dramatically reduce the interpretability of the algorithm. Okay, so in the next video I will explain in Thai.